Here we are at the second lecture of Chem 351, Physical Chemistry. This is the first part of the second lecture, Lecture 2a. In this part, we'll learn how to calculate Q and W, W for the specific case where you have pressure volume work being done. All right, now let's first talk about work, how to calculate W work. And let's take the case where you have pressure volume work. What do I mean by that? Well, let's draw the typical physical chemistry pressure volume work device. What we have here is a piston, and we can move this piston up or down. And in here we would have typically a gas. We're only going to look at gases in this first part. So our system here is a gas, and this then is a system. So we can do work on the system by pushing down on this piston and compressing the gas, or conversely, the gas, the system, can do work on the surroundings by expanding, pushing up on this piston and doing work on the surroundings. Recall that this part here is a system, so everything else up here will be the surroundings. All right, so that's pressure volume work, PV work on a gas. Okay, now if we want to look at the energy change, this is how you calculate that. Work is minus the integral of P dV. So for this work, for this system here, work will be equal to minus the integral of P dV. All right, so you might want to ask, why do you have a negative? All right, well, let's look at this. Suppose that you have a dV, or another way, if you look at finite changes, delta V, is, say, greater than 0. All right, so that means that the initial volume, or the final volume, is greater than the initial. So this means that delta V will be equal to, or actually let's put it this way, delta V will be greater than 0. So the final minus initial, the final volume is greater than initial. Delta V here will be 0, or greater than 0. Or if we look at a differential, dV will be greater than 0, the change in volume. All right. Now, before we go on, let's talk about a convention that people use. We say that energy change, which for instance will be Q or W, will be greater than 0 if the system gains energy. And E, it could be like Q or W, will be less than 0 if the system loses energy. So in other words, this is a system-centric convention. All right, so here's our universe, here's our system. Now, if the energy, actually we should be writing dE or delta E. So if the energy change is greater than 0, then the system has gained energy. In other words, if energy flows from the surroundings into the system gains energy, and we'll say that the change in energy is greater than 0. So in this case, dE is greater than 0. If, on the other hand, the energy flows from the system to the surroundings, E, energy goes away from the system has lost energy, so dE there will be less than 0. The system has lost energy. So it is as if you're sitting inside the system and saying, am I gaining energy? If I am, then my change in energy is positive. Or am I losing energy? If I'm losing energy, then my change in energy is negative. So this is a convention. I don't know who actually decided to do this, but sort of makes sense. You're sitting in the system, and energy comes to you, or you do energy flows from you into the surroundings. All right, so with that convention, let's go back up here. Now suppose that delta V is greater than 0. Delta V is greater than 0 means the piston expanded. So the gas must have done work on the surroundings. The gas did work on the surroundings. It lost energy. So therefore dE for this for dV to be greater than 0 must be dE must be less than 0, because you're losing energy, you're expanding the volume of the gas. If on the other hand, what about dE for dV less than 0? All right, dV less than 0 means the change of the gas, the system, is negative. In other words, the surroundings are pushing down on this piston to decrease the volume of the gas to give a dV negative. But we're sitting in the system here, the gas, and we're gaining energy. The surroundings are doing work on us. So a dV less than 0 means we're gaining energy. So this implies that dE has to be greater than 0. So the sign of delta V has to be different from the work or the energy. In this case, we're talking about work. So if dV is positive, we put that negative sign there to make the work negative. Or if dV is negative, some positive will make this negative, and so on. So that's why the negative, because of our convention that energy changes. Hello, where'd this go? Yeah, there it is. Because our energy changes, we're sitting in the system. All right, so that's why there's a negative. A slight digression, but I hope we reinforce the idea of system exchanging energy with surroundings. Okay, so that's how you calculate work, PV work on a gas done by the gas or done on the gas, minus the integral of PdV. And this integral, if we want to make it definite, will be from the initial volume, V1, to the final volume, V2. Okay, so that's a definite integral. All right, so I hope we understand that. Now let's do a couple examples to see if we really understand it. First example, calculate the work done by an ideal gas when it expands from 1 liter to 2 liter against a constant external pressure of 1 atmosphere. Okay, so if we again look at our standard physical chemistry diagram of pressure volume work done on or by gases, this is the piston. You can go up or down. And by the way, this is frictionless piston, the typical frictionless piston that you might find in physics. So we have initial volume V1 to be 1 liter, and the final volume, we use subscript 2 for the final volume, will be 2 liters, and the pressure is constant at 1 atmosphere. All right, so here we have a constant pressure, and V1 initially is 1 liter, and finally it's 2 liter. So the gas must have done work on the surroundings by expanding this, pushing this piston up. This piston goes up, and therefore it's losing energy, so our energy change should be negative. All right, let's go ahead and use our definition of how to calculate work done minus the integral of PdV. Now pressure is a constant, so that means we can pull out the pressure minus P, the integral of dV, and we'll again make it definite from V1 to V2. So this would be V1 to V2, and that is equal to minus the pressure. The integral of just dV is just V evaluated between the limits V1 and V2, and that's just equal to minus P, V2 minus V1. Oh look, final minus initial, so we can compactly note this as minus P delta V, where delta means final minus initial. So for a constant pressure, the work done in expanding a gas is minus P delta V. Now let's go ahead and put in the numbers here. The pressure is 1 atmosphere, the constant pressure, get rid of that, minus 1 atmosphere. And the change in volume, the final volume, V2 is 2 liter, minus the initial volume 1 liter. So this is minus 1 units or atmosphere liter. And again, it's a minus sign just as we expected because the gas is expanding, doing work on the surroundings. It's losing energy, so delta E work should be negative. Okay. Now this is a strange unit, but remember when we talked about intensive, extensive, natural variable pairs, we said that the units of pressure times volume is in fact a unit of energy. So let's convert this to a more common unit of energy. In fact, let's use the SI unit of energy, which is joule. So to convert this, let's go to our good friend Google, and we'll say convert 1 liter atmosphere to joules. All right. So we no longer have to think. There it is, 101 joules. So this is equal to minus 101 joule. See, pretty soon this Google will be plugged into our brain and we'll no longer have to think. It'll do the thinking for us. Okay, so there it is. That's how you calculate for constant pressure and a change in volume. How you calculate the work done on the gas or by the gas is just minus P dV, or P delta V. And for this particular case, the work done is a minus 101 joule. All right. Let's go back to the second example. That was the first one. Let's calculate the work done when 1 mole of an ideal gas is taken reversibly from 2 liter to 1 liter at constant temperature. Now, unfortunately, I have slides a little out of order, so let me talk a little bit about reversibly here, and then in the second part of the lecture number 2, we'll look at in more detail reversible and the opposite of it, the irreversible process. Okay, so let's go again, use our standard physical chemistry diagram for PV work. Here it is. There's our ideal frictionless piston, and here we can push up or down as the surroundings or the gas can push up or down. This is the gas, an ideal gas in this particular case. So what we're going to do is to go from 2 liter to 1 liter so that our initial volume is 2 liter and our final volume, V2, is 1 liter. So that means that the gas is compressed. We must be pushing down on this piston. The surroundings are doing work on the system, and therefore we expect the system to gain energy, or dE, in this case that's equal to W. We expect that to be greater than 0. Okay, so let's use our general equation to calculate work for pressure volume minus the integral of P dV. All right, now the key word there was reversible. Let's make it a definite integral from V1 to V2. Reversible means implies that you go from the initial state to the final state by an infinite number of infinitesimal steps. What does that mean? Well, we're going to compress this gas, go from 2 liter to 1 liter, so we very slowly push this piston down from 2 liter to 1 liter, and each step that we push the piston down is an infinitesimal step, and if we do an infinite number of those infinitesimal steps, we eventually get from our initial to our final state. All right, so reversible, you might think, is an ideal process that in fact will take an infinite time to do a truly reversible process. All right, so each time we move this an infinitesimal amount, the pressure of the gas will change along with the volume. So if you change the volume, it changes the pressure. We'll just go back, forgot to mention that this is at constant temperature. So let's have constant temperature. So you push this down a little bit, the volume changes, and also the pressure changes. Push it down a little bit more, the volume changes, the pressure changes, and so on. So that means that pressure is not constant throughout this process. In fact, it depends on volume. How can we figure out how pressure depends on volume for an ideal gas? Well, remember the ideal gas law. P is equal to nRT over V. So you want to do this because our integrating variable here is volume, so we have to know how pressure depends on volume. So this is minus the integral, definite from V1 to V2, of nRT over V dV. Now we can integrate this. N is, let's see, 1 mole. We're not adding it, so N is a constant. T is a constant. And R, the gas constant, is also a constant. So we can pull this out to be minus nRT times the natural log of, sorry, get a little ahead of myself. Well, I'm going very slowly with these integrals here. We'll speed it up during the as the semester rolls along, but I found that quite a few students are a little rusty in calculus, so we'll go really slowly at first. So this will be the integral, definite integral from V1 to V2 of 1 over V, we pulled everything out, dV. All right, so that's equal to minus nRT, the integral, definite from V1 to V2 of, oh, I just did that. So what is the integral of 1 over V? And you might recall from calculus, the integral of 1 over V dV will be natural log of V evaluated between the two limits of V1 and V2. And this will be minus nRT, natural log of V2 minus ln of V1, or it can be written more precisely as minus nRT times the natural log of V2 final volume over initial volume V1. So this is how you calculate work for reversible expansion of an ideal gas. Minus nRT, natural log of final volume over the initial volume. All right, let's go ahead and calculate for this particular case. We could put in the numbers here. So W, we said, was minus nRT, natural log of V2 over V1. Well, let's see, minus, what is N? N is number of moles. We have 1 mole. What is R? Well, I'll just use the wrong units of R just to show you why. It's not going to work. Remember, from the gas constant is 0.0821 liter atmosphere per mole Kelvin. This is incorrect. Incorrect units for R, but I'm just showing it. T, Kelvin, we have to worry about Kelvin, so that's 25 plus 273. That's T in Kelvin, add 273.15, times the natural log of the volume ratio. So initially it's 2 liter, finally it's 1 liter. So the final volume, V2, is 1 liter. The initial volume is 2 liter. So there it is. Now let's sort of look at units here. Okay, the mole is going to cancel out. The Kelvin, this is in Kelvin, I forgot to put the units there. Kelvin is going to cancel out. But here we have liter atmosphere, and here we have natural log of unit. Logs or exponents, as you may remember, do not have units, strictly speaking. So this is unitless. So we can calculate this out, and what we will get will be some number in liter atmosphere, which is an odd unit. It's a valid unit for energy, but it's an odd unit. It's not an SI unit. We can avoid that conversion like we did before, going from liter atmosphere to joule. Remember, Google said that 1 liter atmosphere is 101 joule. We use that as a conversion factor we want, but here's a better way. Let's use a different value of the gas constant. So 1 mole, let's use 8.314 joule per mole Kelvin. Okay, so this, when the mole will cancel out, here we have 25 plus 273 Kelvin, and here we have natural log of 1/2. The liters will cancel out. So now the mole will cancel out, the Kelvin will cancel out, and our units will be in joule. So we can save ourselves a conversion factor by using the more common units of R, 8.314 joule per mole Kelvin. So we actually calculate that. That comes out to be, and note that the logarithm of a number less than 1 is negative. So this is a negative number, which will cancel out, oops, I forgot to carry my negatives here, which will cancel out that negative, give a positive, as we expected at the very beginning, 1.72 times 10 to the third joule. Forgot that negative, sorry. Okay, so that's how much energy is done on the system when you compress the gas from 2 liter to 1 liter, constant temperature 25 degree, constant number of moles 1 mole. All right. So in general, then, constant pressure work is equal to minus delta V. For reversible, constant T, N, and ideal gas. So here we're putting a bunch of restrictions on. Work is minus nRT times the natural log of the final volume over the initial volume. Now typically that's what happens in chemistry, physical chemistry. You deal with a general equation, and then you start putting on restrictions to that general equation, and you get these tractable, nice compact forms for calculate, in this case, work. Okay. Let's do one more example. Actually, no, that was work. Let's do an example of calculating Q. Now, you might remember from introductory chemistry, Q is here C, which is heat capacity. And we'll talk in the second part of this lecture more about heat capacity. Capacity to hold heat. And here is a delta, means T final minus T initial. Here, lowercase c is the specific heat, which is the heat capacity per gram, and here m then would be mass. So this is typically a way you would use to calculate Q. You do a measurement, see how much the temperature changed, and multiply that by the heat capacity, or the heat capacity, the specific heat times mass, which gives you the heat capacity. Okay, let's apply this equation to calculate Q for this example. This example actually is right out of introductory chemistry, but we'll review it anyway. I have a 7.5 gram piece of iron, and this is at 100 degrees. And you drop that into 25 grams of water, 22 degrees. What is Q for the iron? The specific heat capacity of iron and water are this. Okay, so what is Q for the iron? Let's see. Q for the iron, let's use this, will be the heat capacity times delta T. But we're not given final, and we're not given actually initial. Well, we're given the initial temperature of the iron, but now given the final temperature of the iron. So here we have to use calorimetry and first law concepts. All right, so let's do that. Oh, picture's worth 1,000 words. So here we're going to draw our universe. Our universe is the calorimeter. So if we go back here, I guess that getting a little ahead of myself. All right. Ignore that. That's for the next example. All right. So let's look at this. Look at it this way. Here's the iron up here, and it is at 100 degrees C. Down here is water, and it is at what do we say 22 degrees. And here, can't draw very well tonight, so let's try it again. Felt tip pen. So, and this is at 22 degrees C. And we said that this was 7.5 grams of iron, and this was 25 grams of water. Now note that there's a temperature gradient. Yes, there's a temperature gradient. So this is 100 degrees, this is 22 degrees, and so heat is going to flow from this temperature gradient. The iron is going to cool off and the water is going to heat up. And let's make this insulated. So the only way the heat can flow is from the iron to the water. It can't get out of here. All right, so let's try to figure out what's happening here. Well, we know that since this is insulated, the Q for the iron is equal to minus Q of the water. So the heat lost by the iron is the heat gained by water. We're not doing any work, there's no expansion, so the energy change is just this Q that's transferred. And by the first law of thermodynamics, this is insulated, isolated system, consider it. The heat lost here has to equal the heat gained here. Or I should put the minus sign the other way. All right, so let's talk about the heat lost by iron, QFE. Well, that is equal to, from our previous equation here, let's see, we're given the specific heat capacity of iron. So we'll use this second form to calculate Q, mc delta T. mc delta T. So M is 7.5 gram. The specific heat given in the problem was 0.45 joule per gram Kelvin. Okay, 0.55 joule per gram Kelvin. And the delta T is the final temperature. We don't know what the final temperature is, minus the initial temperature, which was 100 degrees C. And similarly, Q for water, we'll use that again as mc delta T. We're going to use that form because we're given the specific heat capacity of water, 4.184 joule per gram per Kelvin. All right, so we have 25 grams of water. The specific heat capacity is 4.184 joule per gram Kelvin. And here we have the final temperature minus the initial temperature, 22 degrees C. So we don't know what the final temperature is, but we do know what the initial temperature is. How do we calculate the final temperature? Well, let's put this here, and let's equate that to minus there, minus Q. So what we have is one equation. When we substitute these things in here, is one equation with one unknown. That's the final temperature. And if you go ahead, and I won't work it, so I won't work it out here, but the final temperature comes out to be 22.5 degrees C. Now with the final temperature, we can go ahead and calculate Q for iron. Q for iron is the mass of iron, 7.5 gram, times the specific heat capacity of iron, which is 0.45 joule per gram per Kelvin. And the final temperature, 22.5 degrees C, minus the initial temperature of the iron was 100 degrees C. And this comes out to be 2.6 times 10 to the second joule. And note that this is a negative sign here, so it's minus. Now let me make that more clear here. Oh, I love the eraser feature. That's equal to minus 2.6 times 10 to the squared. And we expected a negative heat for iron because, again, our sign convention, we're sitting here in the iron. Q is negative because iron is losing heat. And similarly, Q for water will be positive. And in fact, Q for water will be exactly the negative of Q for iron. So Q for water will then be plus 2.6 times 10 squared joule, because Q is the only form of energy that's transferred, and it's an isolated or insulated container, and therefore the Q lost by the iron has to equal Q gained by the water. Okay, so that's that example. That's generally how you calculate Q. You have to know heat capacity or a specific heat times mass. Actually, let's go back here. Now you're probably wondering, here we have Kelvin, but here we have degrees C. So you're probably wondering, what's going on here? Well, I'm going to claim that a delta T in Kelvin is equal to a delta T in degrees C. All right, let's convert, in fact, degrees C to Kelvin. So we have, say T. I'll just use real units here and real numbers. Okay, so suppose we have our temperature, first temperature T1 is equal to say 25 degrees C, and say T2 is equal to 50 degrees C. So delta T in degrees C will be equal to the final temperature 50 degrees C minus 25 degrees C, and that's 25 degrees C. Now let's convert all these temperatures to Kelvin. So let's do a delta T in Kelvin. Well, that will be 50 plus 273. So now we've converted this to Kelvin by adding 273 minus a final minus initial minus 25 plus 273. That's in Kelvin. So this would be in Kelvin. But note that this would be 50 minus 25 plus 273 minus 273. So that will cancel out, and we'll just get 25 Kelvin. So a delta T in Kelvin is a delta T in degrees C. So that's why we used the degree C here in Kelvin. This delta here was the same regardless of whether we used degree C or Kelvin. Okay, that's that. And one other point I want to make here. Heat capacity, well, yeah, let's do it this way. So heat capacity C, that's heat capacity. If you take, and that has units of joule per Kelvin, as you may remember from introductory chemistry. Let's look at mass times lowercase c, which is specific heat capacity. I claim that m times lowercase c, specific heat capacity, is also a heat capacity. All right, so mass, let's express that in terms of gram. All right, specific heat is joule per gram Kelvin. So in fact, if you multiply mass times specific heat, you'll get joule per Kelvin, which is heat capacity. All right, so based on this unit argument, mass times specific heat is equal to heat capacity. Okay, so those are the extra points I wanted to make on this example. All right, one more example. Here we have glucose is burned in a bomb calorimeter. A bomb calorimeter is a constant volume calorimeter. The calorimeter has a heat capacity of 641 joule per Kelvin. When this much glucose is burned, the temperature of the calorimeter increases by 7.793. And one thing that's missing here is that there's water in the calorimeter. Actually, we don't need that, so ignore just what I said. Okay, so if one considers the chemical reaction as the system, what is the sign of Q? All right, what is the sign of Q? Well, let's draw a picture here. Here's our calorimeter. As I try to draw this in the last. Okay, so calorimeter. And maybe you remember from introductory chemistry, we used like a coffee cup calorimeter. Essentially, this is insulated, so no heat can go outside the calorimeter, and is a constant volume, so this is also rigid, so there's no possibility of PV work. Remember, work is minus the integral of P dV, and if it's rigid, that means constant volume, a bomb calorimeter is rigid. This implies dV is equal to 0, which implies work is equal to 0. So there's no work. So essentially there's a little mini universe in which heat can go from one place to another. And our system, as we suggested in the problem, our system was a chemical reaction, C6H12O6, that's glucose, and we're going to burn that in in oxygen, to produce, let's see, 6H2O plus 6 CO2, and that's 6, 12, 18, 6, 12 divided by 2, 6. There's a balanced chemical equation. All right, so there is our system. Our system is the chemical reaction. All right, so that's abstracted out. And then the calorimeter, typically you have water in a calorimeter and something like that. But here, delta T, given an example, delta T is a positive number. Delta T for the calorimeter, 7.793. So delta T in here, in the calorimeter, the temperature went up. What does that mean? For the temperature to go up, Q must have gone from the chemical reaction into the surroundings, into the calorimeter, in order to increase the temperature of the calorimeter. So if Q is lost from the system, this means that Q, and we're considering the chemical reaction as a system, Q is less than 0. Okay, and calculate Q for the reaction. Okay, let's do that. So Q for the reaction is equal to minus Q of the calorimeter. Why is that? Again, it's like a first law argument. This is a mini universe isolated from anything else, and so any energy changes here, if Q is lost here in the system, it has to be picked up here in the surroundings, which are isolated from anything else. So the heat lost here is equal to heat gained there. First law argument. So Q reaction is minus Q calorimeter. How do you calculate Q calorimeter? Okay, we know the heat capacity, 641 joule per Kelvin, minus 641 joule per Kelvin. That's a heat capacity, not a specific heat. It's just joule per Kelvin. And let's look at delta T, final minus initial. Well, it's already given, 7.793. And that is in degree C. That's also in Kelvin. Let's write it in Kelvin this time so things cancel out. So we calculate this out, and we get 5.0 times 10 to the third joule with a minus sign. Keep forgetting that minus sign there, with a minus sign. All right, minus sign carries over. This is a positive number. So the energy or the heat transferred in the reaction is minus 5.0 times 10 to the third. Note that here Q is less than 0 for the reaction. This implies that the reaction is exothermic. In other words, the surroundings heat up. That's just what we have here. It's exothermic. The surroundings heated up. It heated up by 7.793 delta T. Okay, so in summary, we have now a couple ways to calculate work done going from an initial state to a final state, or heat transferred going from initial to final state. All right, so that's the end of this first part of the second lecture. Hope you had a good time listening to it.